everybody, getting ready to do lesson 3.5 part 1 of pre-calculus math today. If you need note-taking guides, videos, or PowerPoints, email me here. Those out to you. 3.5 part 1. We got 54 points here in classwork, and you got 0 points here to go in your notebook. 3.5 exponential and logarithmic models. Teachers, today's bell work is right here. Use the leading coefficient test to determine the right-hand, left-hand behavior of the graph of the polynomial function. So students, do this. You can use your grids here as a reference. Give your students 3-4 minutes for that. Okay, welcome back for the solutions of today's bell work. The leading coefficient test for these, the graph falls to the left and rises to the right. Your leading coefficient would be 2, so it falls to the left and it rises to the right, so it goes something like that. And then here we have a -4 as your leading coefficient there, so the graph falls to the left and falls to the right. So usually these graphs have a bump there and then they fall back down again because of the negative here, -4. It's even, and then this is a positive even, so this is the characteristic of that, if you'll remember that from your Algebra 2. Moving on into our first page today, students, in your notebook. Put this in. There are many examples of exponential and logarithmic models in real life. In 3.1, you use the formula A equals PE to the RT. This is an exponential model for continuous growth. To find the balance in an account when interest was compounded continuously. In 3.2 example 10, you used a human memory model. And this is the logarithmic function that was used to determine human memory as time, in respect to time for that. So write this down, students. There's a good reference here for you to remember this and to remember this. Logarithmic model here. Okay, page 2 into your notebook. The 5 most common types of mathematical models involving exponential functions or logarithmic functions are as follows. Exponential growth model, here's an example here of that. Number 2, exponential decay, where now your leading part of your exponent is negative, so there'll be a decay model. And then the Gaussian model is this. So this goes in your notebook, students. Write these formulas down. And then logistic growth model would be this formula here. And then number 5 would be logarithmic models, A plus B, natural log X. So write these down. We'll be using these throughout this course. 2 points, slide number 2, your notebook. And then here's another example here of a logarithmic model. Y equals A plus B log base 10x. There will be another one here. Instead of your base being a natural log, it would be log 10, common log. Okay, moving into our first classwork page here. The basic shapes of these graphs are shown here. So here's an exponential growth model graph there. And then here's exponential decay. It's falling now from left to right. And then the Gaussian model looks like a standard normal curve that you'd use a lot in statistics. This is your classwork sheet page 4, the basic shapes of these graphs. Again, we have a logistic growth model here. This is the logistic growth model here. And then the natural log model would be this here, natural log. And then the common log is here. So Again, this is a class worksheet, slide number 4. You can often gain quite a bit of insight into a situation modeled by an exponential or log function by identifying and interpreting the function's asymptote. So we have asymptote here, here's an asymptote, here's an asymptote. Page 5 in your classwork. First example, demography, exponential growth and decay. Estimates of the world population in millions from 2003 through 2009 are shown in the table. A scatter plot of the data is shown. So here's your scatter plot derived from this table here. An exponential growth model that approximates these data is given by, and then here is your function that describes this relation here. 3 is less than or equal to t is less than or equal to 9, 2003, 2009, where p is the population in millions and t equals 3 represents 2003. Compare the values given by the model with the estimates shown in the table according to this model. So these are estimates here through 2009, and then this is a function here that approximates these data. So does the table match what the function portrays here as a question? And it should, shouldn't it? Why wouldn't it? When will the world population reach 7.1 billion? So here, up to 2009, we're at 67, 68. So we're not quite at 7.1. So from the table appears the model is a good fit. So here's the model, and then the population. Pretty good. The model's falling down here a little bit, kind of lax. The population's better increasing. Well, here it evens out though. So when will the world reach 7.1? So p equals 7100. So we plug that into our when will that happen? So 6097e equals 0.0116 to the t equals p. And now we're going to plug in 7100 for p and see the time for when that will happen. So when we do that, what do we do here? To do this, we divide both sides by 6097. Now we're going to take a natural log of each side, and when we do that, this becomes 0.116t equals 0.15230. Inverse property here, taking natural logs of this, and then we took the natural log of that there. So t equals 13.1. So when we do that division, so it would be 2013 when it would reach 7.1 billion. So your graphical solution will be right here. This would be your graphical solution that you put this into your graphing calculator by using this model here. And then when x equals 9, we got 67, 68 about for that. And then when y equals 7100, we're going to make a flat line here at y equals 7100 on your graphing calculator, and then see where they intersect here. And it intersects at a little over 13.129. So it'll be 2013, a little over 2013 when it reaches 7.1 billion according to that model. So that's an example of using a model. Okay, so according to the model, when will the population of Pittsburgh be approximately 2,900? So going back to that, the populations P in thousands of Pittsburgh, Pennsylvania from 2000 to 2008 can be modeled. Here's the model for the population growth of Pittsburgh, which is falling. According to the model, was the population of Pittsburgh increasing or decreasing from 2000 to 2008? Explain your reasoning. So to respond to this, right, you can tell from the model that it's decreasing because the coefficient's negative here for the exponent. So for 2000, let t equal 0. So when we do that, we have 333,680. And then for 2005, let t equal 5. You plug that in, and now we're down to 317,565. 2008 is 308,272. So it is, Pittsburgh is losing people. According to the model, when will the population of Pittsburgh be approximately 290? So again, we make p equals 290 and then solve for t here. And so we divide through first. And then we take the natural log of both sides, and we add natural log of this quantity here. Will give us, we take the natural log of the numerator, and then we divide through by negative 0.0099. And when you get through crunching that number in your calculator, you get 14.17 or 2014, according to that population model there. Okay, so that's a cool way of using a population model. Example 2, modeling population growth. Research experiment. Population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300. How many flies will there be after 5 days? So let y be the number of flies at time t in days. From the given information, you know that y equals 100. So 100 flies. T equals 2. How many flies will there be after 2 days? After 2 days, there are 100 flies. And then, y equals 300 after 4 days. So we have some data here that we can plug into an exponential model to really come down with a function that models this population growth. Substituting this information into the model, y equals ae to the bt produces 100 equals ae to b, because we have 100 flies at 2 days. So it would be 2b here. We just moved our t over here, 2 days for that. And we got 300 flies after 4 days, ae to the 4b. So now we have 2 points on our exponential function. To solve for b, we need to solve for b here. Solve for a in the first. So we're going to solve for the first equation there, that first exponential equation. So 100 equals ae to b, and then this becomes a, when we isolate a here, we get a equals 100 over e to the 2b. So that's a. Then substitute the result into the second. So when here's our second here, 300 equals ae to the 4b. We know what a is. So we substitute that in to this equation here. 300 equals 100 over e to the 2b, that's our a, times e to the 4b. So we substituted this for a. Once we do that, then we continue to solve here. 300 equals 100 e to the 2b. We simplified the initial expression. Divided through by 100. 3 equals e to the 2b. Now we're going to take the natural log of both sides. And when we do that, we have natural log 3 equals 2b. Then we continue to solve for b here. 1/2 of natural log 3 would equal b. And when we solve for that, b equals 1/2 natural log 3 in the equation you found for a. So a equals 100 e to the 2b. So we can plug that into a now. So we can plug our solution that we found in the second back into the first. So a equals 100 e to the 2b. Here is b right here, 1/2 natural log 3. So when we solve for that, we get 100 over e to natural log 3, 100 over natural log 3, and then when we continue to simplify that, we get 100 over 3, and that becomes 33.33 for A. A equals 33.33. So what do we do with that? So 33.33 in B equals 1/2 natural log 3, which equals this amount here for B. The exponential growth model is y equals 33.33 e to the 0.5493 t. Now we've got this solved for t in terms of t. So when we put that into our calculator, this is what your curve looks like. So this implies that after 5 days, which is here, you will have, guess how many flies? You'll have 520 flies using that population model between these two data points here. This would continue up like that. So that would be how you would form a exponential model from 2 data points. Usually you wouldn't want more, but in this case that's what we're going to do. So now populations in thousands, San Antonio, Texas, from 2000 to 2008 can be modeled by this function here, where t is the year, with t equals 0 corresponding to 2000. In 2002, the population was 1,200. Find the value of k for the model, round your result to 4 decimal places. So, and then use your model to predict the population in 2015. Okay, so to do this, we did basically what we did with the fruit flies. We have 2002, t equals 2, the population was 1.2 million, p equals 1,200, this will be in thousands here, in thousands, p is in thousands. So we plug that into our original function up here, and we want to solve for k here. So 2k, we have this is our original here, and then we're going to divide through by 1155.4 both sides, and then we're going to take the natural log of both sides to get rid of our e over here. So natural log this quantity there equals k, then we divide through by 2, so we will have 1/2 natural log 1200 over 1155.4 equals k, and then this quantity becomes 0.0189 equals k, so p would equal 1155.4e to the 0.0189 t. So we solve for k, our k factor there, and then now we have it solved for t. So we can predict now what, using that model, what the population will be in 2015. So let t equal 15 and then find p. So we have p here. We plug in 15 there for t, and then when we crank that out, we have p equals 1534.104 or 1.534. 104 people in this city, I believe is what it was. So that's how you use a population model that you derive from 2 data points. And as your lesson for today, questions, tutoring, etc., note-taking guides, email me here. Thank you very much.